Okay, so the plan here is to do a proof of concept of a super minimal basic example of how you can force two objects to collide in Unity. So I'm going to go ahead in my 3D new project in the sample scene space, right click 3D object sphere. There's my new sphere. I will rename him sphere 1. Control D to make a duplicate, rename that to sphere 2, and then drag him over, and voila, we have two spheres. Move him in X, Y, and Z so there's some variety in their positions. And I'll real quick in the assets create material, call this one blue, change its color to blue. Whoops, that didn't take, there we go. That'll be blue, and one more, create material, call it red, and make it red. Drag it onto the object in the scene. Okay, so there's two spheres, red and blue. Sphere 1 is where I will put all the action, all the logic. So I'll add a component over here, and I'm going to call it come together. New script, come together, and then it's available in the assets here. And what we're going to need is, so I'm actually kind of a novice with Unity, but I'm good with physics and I've been programming a long time, so I figured this out and I figured it'd be useful because when I googled it, it didn't come up quickly for me. But anyway, what we're going to need is a public object within the come together class, and we can grab a transform type and call it P1, and likewise for P2. So transforms, I save that, minimize. Transforms are grabbing the information from up here on an object, on a game object, so it holds a position, rotation, scale, and some other metadata. But now that I have added the transform to the class come together, they're available here in the workspace. So if we click sphere 1 way on the left, drag it over into P1, there's now a link. P1, the variable in the code, is now attached to the sphere 1 object in the game, and P2 to sphere 2 now. So if we come back and click this, we don't really need anything to happen at startup. It'll just happen every frame. And we'll say debug.log P1 position and P1.position should give us the position at every frame for that first sphere. So I saved that. Let's play it. And going to the console, indeed there's a position. Moving sphere 2 doesn't change the output there. Moving sphere 1 does. So if I move in the X direction, that first number changes. If I move in the Y direction, the second number changes, and in the Z, the third number changes. So I'm tracking in frame by frame the position in 3 dimensions of that object. That's great. Okay, a couple more steps only. Going back to that code, we don't care much about the position, we care about changing it and making these objects collide. So we can store P1, let's say R is a typical letter reserved for positional vectors, so we'll say R1 is of vector 3 type, and it is P1.position. So it's accessing P1, which is a transform type, on our sphere 1 object in the game. That position is a 3-number vector, 3 elements. Do the same thing with R2. So it's going to get that position every frame. Well, the difference between the two is, I'll just call it RDiff, and it's simply R2 minus R1. It's still a 3-element vector with a difference in X, difference in Y, and difference in Z. So that number should change too as you drag around the objects, which real quick, just for proof of concept, I'm trying to be a little bit excessive just to fill in gaps that are things you may not have seen before. but here we'll get the distance at each frame. Hit play. Go to console, and here's R. So if I move this object, the R in the Z direction is changing. That's a good sign. If I move the other object, it should also change, and it does, because we're getting now the distance between the two objects, not simply the position of one of them. Okay, good, good. Going back to our come together script. Don't need to log it. The R vector is a distance vector between two objects, but the direction itself is the normalized difference vector. Normalized means if you sum up the squares of each element, you just add up to 1. So it's normalized in that the direction is the only important piece of information in the numbers, not the magnitude, how big the delta is, just which way it's pointing. So a normalized direction, we can call it, vector, would be vector 3 dot normalize r2 minus r1. And in fact, we already have a vector that contains that, so we can just normalize the difference vector. That'll give us our direction. And once again, for proof of concept's sake, I'll just put that in the log and we'll see how it plans out. Call it r norm. And it's direction, so. Okay, let's see how it goes. Expected a parentheses, of course. Okay. So now if we look at our console, we see the direction. And you can see this number changes as I move the relative position of the two objects, but the sum of the squares of those three numbers is always going to be 1. And those are rounded off to 1/10 of a decimal place. But you get the idea. It's a direction vector, not a raw magnitude vector. And the direction vector is useful because if you multiply it with something else, you can change the direction of another vector, which is kind of what we're getting at. Okay. So finally, we need to move these guys. And to do that, I'm going to use one of the basic physics objects in Unity, which is rigid body. And we'll say body1. There's various, as with everything else, there's various ways to do this, but I'm just kind of doing a quick and dirty exemplar way to do it. Rigid body B1 and B2 are now in the namespace, or in the class, I should say. And we will put sphere 1 to rigid body 1. Oh, we can't do that yet because sphere 1 and sphere 2 need rigid body components. They don't have it by default, so we need to search rigid body, and we have added now a rigid body component. And same for sphere 2, add component, rigid body, and bada bing. After I've added the rigid bodies, if I play this now, you'll see these guys fall due to gravity. And I kind of like that effect to just spice things up and prove that this collision thing works. So I'm going to keep them there, and I'm going to add one more thing to the space, which is 3D object, cube, move him down a little bit, and change his scale in X to 50, and in Z, I think, yeah, to 50, so there's a floor. And in fact, I'll call him a floor. And one more thing with the floor, let's make him a rigid body too. And down here in constraints for rigid body, I will freeze the position and rotation of XYZ just so that it just ain't gonna move. I think actually it might move. I'm not, like, again, a super Unity expert, but that at least applies constraints absent of external forces to the floor. So if we play now, we see, yeah, these guys just hit the floor and there's nothing more. Okay. Next, come together. We have our direction vector between the two spheres, which is recorded at every frame. Now we want to move the two spheres to approach each other. So to do that, we're going to access well, to do that first, let's calculate the force that we're going to apply. So vector 3, I'll call it F for force, and it's going to be the direction vector, which points it in the right way, times some magnitude that we could choose at will. So I'll just pick 100 for now. And if we do that, that's a force that's in the direction of sphere 2 towards sphere 1. And so now if I access the rigid body B1, which again was up here, and we assign to sphere 1, and we add force to that rigid body, and we pass in F, which is a 3-part number, which is in the direction of the distance between them line, and times 100. This should apply a force to B1. Just for sake of example, I'm going to do the exact same thing real quick, and I know it will be wrong, but I'm going to do it just to show you what it looks like if I apply the same force to both of them. So if we apply the same force to both of them, play this out, you can see not anything. Oh, B1 has not been assigned. Ah yes, I didn't link the come together script objects, so B1 should be sphere 1, B2 should be sphere 2. Okay, so now let's play. And for the sake of learning, boom. The two spheres go in the same direction, but if you notice the direction they fly is the line between them. So if I move this over here, they'll fly in that line's direction. Okay, so we're almost there. I could, with one character now, just fix this issue. If I put a minus force, it's going to be the same line in the opposite direction. So if we do that, save, go back, and play, now these two spheres are both at every frame being pushed in the line of direction of each other in opposite directions, which basically means they are stuck together. And as you can see, when I shove it a little bit, it inevitably just comes back together. So every frame it's sticking together. The only other little nuance here, which you've probably seen before if you spend any amount of time learning this stuff, is when you use forces in Unity, it's good to normalize them by this variable time delta time. Time delta time is equal to 1 divided by the frame rate of your monitor. And so we could display that. This is just like a side thing, but I found it useful when I realized what it was. Time delta time is time dot delta time. So that would be time dot delta time. We'd put that in the log. It's not very intuitive what that is, but if we say now the frames per second is 1 over that, and print that to the log, we will finally see this number, which is for me close to 144 all the time, which is about the refresh rate of my monitor. So time.delta time is the inverse of your frame rate. So if you multiply the inverse of your frame rate by the forces you're applying to objects, it means that no matter the frame rate of the person who's playing the game, you're going to have consistent simulated results across all those devices. So that's important every time you apply a force. So that's it. That's how you force two objects to collide. You can see how this might extend into other things, and I think I'll actually make videos on following up with this, kind of toying with it. But if you appreciated this, go ahead and like and subscribe, because this is something I wish I had access to or had easily seen in the past, and I think that if it benefits you guys, it would encourage me to make some more stuff in the future. Alright, good luck, and see you next time.